I recently went to Calgary, Alberta to visit my grandparents, and just as the spring comes around, they wanted to start planting in their garden again. And they have a pretty nice garden, but there were some problems with the soil. So I decided to kind of make it a fun little project to see if I could use some of the knowledge that I have about soil to help them grow more food this coming summer.
So here is our soil. We have many plots to be planting some horticultural plants on. This is a soil in Alberta, which is a very dry area. So my first hypothesis is that the soil might be salt affected, and you can see how dry it is. When a soil gets that dry in an arid or semi-arid environment, it doesn't have as much rainfall, obviously, and it can't be leached as much. So the salt content kind of rises as water keeps evaporating and keeps not draining the salt. The other thing that can happen to an extremely salt-affected soil is it can become what's called sodic, which is where the exchange sites on the mineral soils are filled with too much sodium ions. So that's also really bad for plants, and it causes the pH of the soil to be too high. In Alberta, we usually have high pH soils naturally, but just like anything, too much of a good thing is a bad thing. And high pH is usually pretty good for plants until it gets to a upper limit. Unfortunately, I don't have an EC tester, an electric conductivity tester, which is usually how we would determine if the soil is salt affected. But I have a plan for how I'm going to test that myself, and I'm going to look at the plants, mostly weeds that are growing here, and see what their traditional salt tolerance is and sodium tolerance. And then based on that, I can kind of figure out if these soils are salt affected or not. I'm also going to test the pH of the soil, but I also don't have a pH electrode or a pH tester for soil. So what I'm going to do is a home test using vinegar and a visual gauge of how alkaline or acidic the soil is. Okay, so I'm going to get 2 tablespoons of soil. The soil's very dry. Maybe I'll go a little extra. Go. Okay, now we're in the kitchen, and we have our bowl of soil, and we have white vinegar, also known as acetic acid. Many of you, when you were a kid, you might have done a little science experiment where you mix baking soda with vinegar, and it bubbles a lot. It kind of creates like a volcano eruption. That's because baking soda is basic and vinegar is acidic. So we're going to see what happens if we pour a little bit of vinegar. If it bubbles a lot, that means that this soil should be alkaline, should be basic. If it doesn't bubble, we won't really see any reaction between the acidic and acidic. So we're definitely seeing some bubbling here. We're seeing a decent amount of bubbling, which means we can be pretty sure that the pH is over 7. My original thoughts were that this soil might be salt affected, but typically salt affected soils have they don't have a strongly alkaline pH. But we saw from the way that this soil reacted with vinegar that it seems to be pretty strongly alkaline. The other possibility is that this soil might be sodic, which means that it has an abundance of sodium ions in the exchange sites of the clay. So we'll take a look at that. So sodic soils are soils that have an excess amount of sodium ions in their clay exchange sites. In this soil here, we can see there's almost no organic matter, so we can really clearly see the expression of the clay. We can see there's cracks, which will happen when the clay dries out and is dehydrated. And then when the clay is hydrated, because the sodium ion tends to hold a lot of water around it in the exchange sites of the clay, it disperses and the clay swells a lot and it becomes poorly drained. So So that's something that we'll definitely have to fix in these soils if we want to have a good harvest. One of the best solutions for sodic soils is to use gypsum as a lime. So when we use gypsum on a sodic soil, what we're doing is we're replacing the exchange sites that are full of sodium ions, we're replacing them with calcium ions, which are less hydrating, so they'll cause the clay to shrink and swell a little bit less, which will make it better drained and also not as easily dried up, not as easily dehydrated.
The chemical formula for gypsum is CaSO4 plus 2H2O. Gypsum is a neutral salt, which means it's the product of a reaction between a strong acid, usually sulfuric acid, and a strong base, usually calcium hydroxide. We don't want to make the pH of this soil any higher than it already is. Like we saw, it's pretty high. So that's why we use a neutral salt. In an agricultural scenario, we definitely want to do some calculations to figure out how much gypsum we want to put on the fields. Unfortunately, though, we don't have very sophisticated testing equipment. You saw my vinegar test earlier. I don't have an electric conductivity meter, and I don't have lab equipment to test what the concentration of sodium ions are in the soil. So I just used the last of the gypsum that we had in the garage, and I tried to apply it pretty evenly over the area. Now I'm going to do some calculations to figure out how much water I should use to drain this soil. The soil is also very dry, so we're going to have to do some breaking up of the soil, but this is a good opportunity to both let the gypsum incorporate into the soil and to mix the soil up before we put manure and we start planting. The first step of our calculations is figure out the square footage or square meters of the area that we want to leach. One of our squares was 8 feet by 8 feet, which means the total area was 64 square feet. If we want a 12-inch leaching depth, 12 inches is equal to 1 foot. This means the water volume should be 64 square feet times 1 foot, which will be 64 cubic feet. Each cubic foot of soil can hold 7.48 gallons of water, so we need to multiply this number by 64 cubic feet, which equals 479 gallons. 479 gallons is approximately equal to 1,810 liters of water. Using this much water all at once is a bit irresponsible, especially because Alberta is a prairie province and every summer they have quite a significant water deficit. Usually if we're using gypsum to lime a sodic soil, it would be best if we had a subsurface drainage so that the sodium ions that get exchanged and leached out could actually be removed and not just sit in the subsoil. Because we don't have that and we don't have access to unlimited water, more frequent irrigations, small irrigations are recommended, especially because right now the soil is still sodic, the drainage is not going to be great. So as we water this soil more and more and apply gypsum again and again, the soil quality will gradually improve and the drainage will also gradually improve. Unfortunately though, because of no subsurface drainage, those sodium molecules, sodium ions, are still going to be sitting at the bottom, ready to be uplifted when evapotranspiration becomes very high in the middle of the summer and it becomes very dry. So you can see right away some of the water is cooling and it's not draining immediately, which is a classic sign of a sodic soil. So we've addressed the sodium problem, I think, as best we can. We applied gypsum and we leached with water, or drained with water. Now we're going to focus on plant nutrients. So that's where this comes in. So this is some cow manure that we bought, and the most important plant nutrients
in general are NPK. So you can see here, when they have manure, this is showing the ratio of NPK. So you can see P is usually the least abundant, then we have K, and N is the most important plant nutrient, and it's most often the most deficient plant nutrient in most soils. So what we're going to do is we're going to spread this manure on any areas that we want to plant, the areas that we just put gypsum on, and then we're going to use a shovel to incorporate this organic matter into the soil. Like I said at the beginning of the video, this soil has essentially no organic matter. So this NPK in organic forms is going to kind of give a long-lasting base of organic matter that the plants can pull from, and microbes can degrade and turn into mineral forms that plants can use over time. So this is kind of like cow manure is kind of like long-term insurance for nutrients in the soil. The reason I call this type of fertilizer long-term is because of the chemical speciation of all of the nutrients that are in this manure. The N, P, K, and other nutrients that are contained in this fertilizer are in organic forms, which usually means they're in reduced form, and they're not actually immediately available to plants. It's generally agreed in the scientific community that plants can only absorb nutrients when they're in inorganic or mineral forms. Microbes perform oxidation and reduction reactions to turn these organic forms into inorganic forms. So now we've spread the manure, and it's time to incorporate the manure to make sure that it's a good mixture of organic matter and mineral soil. Oh yeah. Oh yeah, take stuff to Canada Post? Perfect. So generally, we want to incorporate 6 inches. Yes. That's the general rule. I can see there's a little earthworm here. Yeah. That's another interesting thing. You know, earthworms are not supposed to exist in Canada, except for on Vancouver Island. They were wiped out completely by the Ice Age, so they're technically an invasive species, and they're not good for our forests. They're good for crops. Yeah. But when earthworms come in, you have to take into account that there are earthworms because they speed up the turnover of nutrients.
Yeah.
So if you're not paying attention to the fact that there are earthworms, the nutrients in the soil can be turned over to mineral form too quickly for the plants to be taking it up. And that's the problem that happens in our forests with earthworms. That's why there's watches that protect against earthworm invasions. Yeah, no. When we incorporate the residue, we give a chance for microbes to degrade the organic material and actually turn it back into inorganic forms, mineral forms that plants can absorb and use for their metabolic processes. Just like plants, microbes need certain nutrients in certain ratios compared to each other. If residues added have sufficient ratios or even excess ratios of the nutrients they need, then there will be a net mineralization and more of that nutrient will become available to plants. Conversely, if residues added have insufficient nutrient ratios, immobilization will occur. Immobilization is when microbes consume inorganic soil nutrients that otherwise could have gone to plants, and they incorporate them into their microbial biomass, into their bodies. So these nutrients that they've absorbed are unavailable to plants until these microbes die and decompose. So I think you can definitely see that compared to when we started, the soil is more moist, more broken up. There's more aggregation, I guess, or it looks more like a agricultural soil now, and it looks like the drainage is getting better now that we've done a little bit of breaking up. And it's also gotten a lot more organic matter now. It's definitely gotten a shade darker, or a value darker, if you will. So the last plan I had was, I knew that the soil was going to be pretty lacking in nitrogen, and I've been learning a lot about nitrogen fixing bacteria and symbiotic relationships that legumes have with these bacteria. So we bought some broad Windsor beans, which are known for being very good nitrogen fixers with their rhizobia. But because we just incorporated organic matter or residue or manure, there's going to be a net immobilization of nitrogen as microbes break that down. So I don't want to plant these beans yet, because when the beans are young, the rhizobia, the nitrogen fixing bacteria, are not active yet. So if we plant these seeds now, in their early growth stage, they might become nitrogen deficient, and it would just be better if we waited about a week to let that immobilization kick in, and then let those microbes die, and eventually let that nitrogen go back into mineral form, which is available to these seeds. After that, the residue that we just incorporated will be a source of nitrogen, but also the nitrogen fixed from these bacteria will not only be a source of nitrogen for the beans, obviously, but there's also research to suggest that when you have nitrogen fixing bacteria in general in the soil, the root nodules can often leak amino acids or other N-containing compounds into the soil, and that can also be a source of nitrogen for nearby plants. So hopefully we're going to plant some of these beans in each of the little squares that we had, and hopefully that will increase nitrogen availability for all the plants that we end up planting here.